In this session, we are going to deal with different kinds of tests of hypothesis. So, majorly, we will do different kinds of hypothesis tests involving the means, involving the variances, and even the proportion. So, we are making a lot of inferences about the populations, parameters, especially the mean, the variances, and the proportions. We are trying to make these kind of inferences regarding the population parameters by performing appropriate hypothesis tests. And most of the cases, these are all standard tests. They have lots and lots of applications in the real world. So we really need to understand for testing what kind of parameter, for making inference relating to what kind of parameter, what kind of hypothesis test is more appropriate. So as an agenda of this session, we would be focusing on what do we really mean by testing all these things, right? And how do we really proceed about doing this process? Then a few important terminology in the process is something that we need to be comfortable with. We will be discussing about what do I mean by critical region. We have already defined it earlier, but critical region for different kinds of tests. Here we will talk about different types of tests which are otherwise called as a two-tailed test or one-tailed test. So what do we mean by a two-tailed test and one-tailed test, and how do we look at the critical region in each of these tests? What are the detailed steps that are involved in testing a hypothesis? So this is the introductory part. Up to here, it would be the introductory part which is common for all kinds of tests. And after that we are starting our tests where we are looking at the tests that are more and more relating to the means of the data, and the tests which are more associated with the differences between the means. So I am doing the test for mean mu naught. Here I am doing the test for mu1 minus mu2, which is the differences between the means. Here I am looking at the test relating to the variance sigma squared. Here I will be talking about the test relating to the proportion theta. Then I am looking at the differences among the k proportions, wherein we would be introducing to the chi-squared kind of a test. So comparing theta 1, theta 2, theta 3, we are doing some kind of comparisons. So when we are doing a comparisons across the multiple proportions, what are the tests that are involved in that? Then from a tabulated frequencies where there are R rows and C columns, how do I really analyze this R by C table, wherein I would again be using a chi-square test in the process? And finally, we would also look at an application called goodness of fit, where also we would be using the chi-square test only. So these are the various aspects that we are going to look at in this session. This is going to be a slightly a longer session covering different aspects relating to different kinds of tests on the various parameters associated with the data. So let's get started with it. So on the introductory front, we are talking about, when I say testing of significance, we are bringing in a statistical test, right? When we use the word tests of significance, it's nothing but it's a statistical test that I am bringing in. So in this statistical test, we will have a null hypothesis H naught, and the null hypothesis, we said that there is a direct equality mu equal to mu naught, right? So there is something that is involving the equality in a null hypothesis. I have to specify what is my critical region alpha, and even an alternate hypothesis. In general, the alternate hypothesis will be a composite alternate hypothesis itself. Either I'll say mu not equal to mu naught, or mu greater than mu naught, or mu less than mu naught. So the alternate hypothesis is generally a composite alternate hypothesis, whereas the null hypothesis in most of the cases is a simple hypothesis where we are setting it as the equality rule. And we know that the size of the critical region is nothing but the level of significance or the probability of type 1 error. So now if you see here, there are three different kinds of alternatives that are there, right? Either mu is not equal to mu naught, mu is greater than mu naught, or mu is less than mu naught. If you look at this, mu is greater than mu naught. It's only one-sided. Similarly, mu is less than mu naught. It is also one-sided. But so alternate hypothesis is all those values which are less than mu naught. Alternate hypothesis means I will reject the null hypothesis only when the mu is greater than mu naught, only on the higher side of mu naught. I will not reject the null hypothesis when it is lesser than the mu naught at all. By whatever extent it is lesser than mu naught, I will not reject the null hypothesis when I am setting my alternative as mu greater than mu naught. So in both these cases, the rejection region, which is nothing but your critical region, right? The critical region is nothing but the zone of the rejection, is only on one side of mu naught. So that's the reason we call them as one-sided alternatives or one-tail test. So here I will do a testing saying my null hypothesis is theta equal to theta naught, but my alternate hypothesis will be either theta is less than theta naught or theta is greater than theta naught. Only on one side we are setting the alternate hypothesis region, or the critical region is only on the one side. If it is theta is less than theta naught, the critical region is only on the left hand tail. If my alternate hypothesis is theta greater than theta naught, then the critical region is only on the right hand tail of the sample distribution. So we are rejecting the null hypothesis when the theta is much smaller than theta naught, or in this case when it is much greater than theta naught only. So these are called as one-sided alternatives. And whereas on the other side I can have two-sided alternatives, right? Because if the null hypothesis is theta equal to theta naught, my alternate hypothesis, if it becomes theta not equal to theta naught, which means it could be less than theta naught or it could be greater than theta naught. So both the alternatives are very much possible here. So I am looking at accepting the null hypothesis when the estimate of theta is very close to theta naught. Even if it is much less than theta naught, or even if it is much greater than theta naught, in both the cases I am rejecting the null hypothesis. My critical region is present on both the sides of the null hypothesis, both the sides of the sampling distribution, where I can reject the null hypothesis. So that's one of the reasons I really need to understand what is my objective. Is it that I am using a two-tailed test as where the alternatives could be on both the sides, or is it that I am using a one-tailed test where my alternatives are either towards the left hand side or towards the right hand side but not both? And if I am going with usage of likelihood ratio technique, the difference between the sample mean and the population mean, I am simply looking at if it is greater than or equal to z alpha by 2 times sigma by root n. I am looking at both the sides both the sides being having the rejection region. So the modulus of x bar minus mu naught, as long as it is greater than z alpha by 2 times sigma by root n, means x bar minus mu naught is lying between minus z alpha by 2 times sigma by root n to z alpha by 2 times sigma by root n. So because of this region, we call this as a two-tailed test, right? If the value is much below this, we'll call it as a rejection region. If it is above this, we call it as a rejection region. Whereas if I'm calling a one-tailed ones, I'll typically have it as only one side. So I'll get it as x bar is less than or equal to mu naught minus z alpha times sigma by root n. Here there is no, the whole alpha is on the one side only. Or it could be x bar is greater than or equal to mu naught plus z alpha times sigma by root n, which is on the higher side. So if my alternate hypothesis is mu less than mu naught, it is like this. If it is mu greater than mu naught, it would be more like this. So this part of it we really need to understand initially, and once we get a comfort level on what are the critical regions for different kinds of tests. This is a critical region where alternate hypothesis is mu is not equal to mu naught. So I am talking about this being one critical region, this being one critical region, and which is saying the mu naught minus z alpha by 2 times sigma by root n, mu naught plus z alpha by 2 times sigma by root n. Now here we are talking about an alternate hypothesis mu greater than mu naught. So the whole of alpha, the size of the critical region alpha is completely on the right hand side only. As long as the mu is greater than mu naught, I am rejecting my null hypothesis. So this is where we are setting mu naught plus z alpha times sigma by root n. And this is the critical region where mu is less than mu naught. Otherwise mu naught minus z alpha times sigma by root n. So in this process, one more important process that we need to understand is what is the critical region for different kinds of tests. And now, just before we get into the real test execution process, we are trying to understand the important things like what are the major test steps that are involved when I am performing a hypothesis testing. The first step is I have to specify my null hypothesis, my alternate hypothesis. So the null hypothesis is always equal to, whereas my alternate hypothesis is either a two-tailed where we are setting it as not equal to, or it could be a one-tailed where it could be a greater than or less than kind of alternate hypothesis. But I have to specify them. Along with that, I have to specify my alpha, which is nothing but the significance level, or typically we call it as the probability of type 1 error. I have to specify my alpha. What is the probability of type 1 error I am ready to allow? If the null hypothesis is true, what is the chance that it would be rejected? I am specifying that to be around alpha. So generally we specify them as 0.05 or 0.01 in many kinds of application. Once we have specified it, I specify the sampling distribution for the data. What is the distribution that I have to go with? Normal distribution, chi-square distribution, what is that? So I have to specify the sampling distribution of the appropriate test statistic. So I have to find out what is the test statistic that I have to use, which one is more appropriate for this testing. If I have to test the means, what is the test statistic that I have to use? If I have to test the difference between the means, what is the test statistic that is appropriate? So I have to understand the appropriate test statistic. I need to use the sampling distribution of the appropriate test statistic. right? We know a lot of test statistics we have dealt in our estimations chapter, in our sampling and estimations chapter. So we know what kind of test statistics to use, especially in the interval estimation. We know for different kinds of purposes we have used different test statistics, and we have used different sampling distributions. We said that z equal to x bar minus mu by sigma by root n. This follows a standard normal distribution. We also said x bar t equal to x bar minus mu by s by root n will follow a t distribution with n minus 1 degrees of freedom. So these are what we are calling as the sampling distributions of these are the test statistics. These are the sampling distributions that are associated with the test statistic, and I also need to find out the critical region of the size alpha with respect to these sampling distribution. So for finding out the critical values, depending on if it is one tail or two tail, I need to have the understanding of z alpha or z alpha by 2. And for many of the real world problems, we talk about the alpha being either 5% or 1%. So most of the times you will find for these things, for all these test statistics, the values are tabulated in the statistical tables, which we can directly use for our simplification purpose. We can determine the value of the test statistic from the sample data. So if this is my test statistic, I have to find this out from my sample data. From my sample data, I'll find this out, and based on this, and depending on the testing process or the sampling distribution, I will have to really check whether this value of the test statistic. Now, if it is a t distribution or a z distribution, let's say I have got my test statistic is this. I would also find out the critical region of the size alpha. Let's say this is the critical region, this is the rejection zone, this is the rejection zone, this is alpha by 2, this is alpha by 2. So I have found out the critical region of size alpha associated with this sampling distribution. I am looking at where is my test statistic falling. Is it falling in the rejection zone or in the critical region, or is it falling in the acceptance region? Based on that, we are either rejecting the null hypothesis or we are not able to reject the null hypothesis. That is what is the typical process that goes into the testing of hypothesis based on for a particular parameter or for some set of parameters based on a sample data. So that is the total steps or process that is involved in the hypothesis testing. But in some cases, rather than going with that, there is one computation also which are generally seen, which are called as p-values. Sometimes people call it as a probability value, tail probability, or sometimes it's also called as the observed level of significance. Alpha is that significance which we are setting, and P is that observed level of significance. What it means is, what is the probability where the null hypothesis is true? I'm trying to find out what is the probability with which I will accept the null hypothesis. The lowest level of significance at which the null hypothesis, if I had set the alpha as 5%, then what is happening? Let's say this is the alpha is 5%, so this will be my critical region, right? Alpha is 5%, this will be my critical region. Now, if my test statistic is here, my test statistic value is here, then it would be rejected because it is in the critical region. But if you say my alpha is only 1%, so it means this would be my critical region. Only this is my critical region. Now in this case, my test statistic is still here, which is in the acceptance region, which is not in the critical region. So I am not able to reject this, reject the null hypothesis in this case at alpha equal to 1%. So what we are saying is, when I am saying a p-value, what is that minimum value of alpha, right? What is this alpha by 2 and what is this alpha by 2, where the null hypothesis gets rejected. When it is 1%, it is not getting rejected. When it is 5%, it is getting rejected. So I want to know what is that minimum value of alpha at which the null hypothesis is getting rejected. That is what we are calling as the p-value. And it is used as a measure of the strength of evidence, right? Two different tests having two different p-values. The one that is having the most, the least kind of a p-value is much more stronger, much more reliable compared to the one that is having a very high values of p. So when I am using the p-value method, my testing of hypothesis slightly differs. This step will continue to be the same. I will formulate my null hypothesis, alternate hypothesis, I will specify the alpha value, I will find out the distribution, I will compute the test statistic. Now what we will see is, once I determine the value of the test statistic, I will find out the p-value also. I will not find out the critical region directly. I will find out the p-value, which means now I know that this is my test statistic, right? I will find out the p-value, means what is that particular value of alpha for which this null hypothesis could be rejected. What is that smallest value of alpha for which the null hypothesis could be rejected? So I will find that as the p-value. I will compare if the p-value is less than or equal to alpha. If it is less than or equal to alpha, so alpha, let's say I have set it at 5%. If my p-value is less than or equal to alpha, I will reject the null hypothesis. But if the p-value is greater than alpha, I will not reject the null hypothesis. I will take my decision in favor of the null hypothesis. So that's how we have to understand the process of hypothesis testing, the procedure that is involved, the steps that are involved, and the way I make my conclusions based on the computation, the test statistic computation I perform, and based on the p-values that I arrive at. Alright. Now let's look at different kinds of tests that are associated with the means. How, if I want to really test the means of a particular data following a normal distribution or not following a normal distribution. So we'll first look at based on the normal distribution. So when I'm using the testing of the means associated with a normal distribution, so there are three things. Either the samples are coming from normal population, right, or they are not large enough to justify normal approximation. Either of them have to be met. The sample is either coming from normal population or it is large enough that a normal approximation can very well be justified. But if these two are not met, then I have non-parametric alternatives as well. But of course, the non-parametric alternatives we are not taking up here, right? But when the data is coming more from a normal distribution, wherein I can expect it to be more and more normal if it is coming from a normal population, or the sample is so large enough that I can justify the normal approximations using the central limit theorem. But if none of these are getting met, I can very well rely on non-parametric alternatives, which go into the non-parametric tests, which are not covered out here. But when we are talking about the non-parametric alternatives, I really don't require any kind of a knowledge regarding the distribution of the population, right? From what distribution the samples are coming from. What is the typical distribution of the population from which the sampling is being done? I really don't need to have any such kind of assumption. When we are talking about the tests regarding the means, I'm testing a null hypothesis mu equal to mu naught, wherein my alternate hypothesis could be a two-tailed test, wherein it would be mu not equal to mu naught, or it could be a one-tailed test where the alternative hypothesis could be either mu greater than mu naught or mu less than mu naught. So this is the null, so I have to specify my null hypothesis and the alternate hypothesis. I am having a random sample of size n, and I am making an assumption that it is a normal population. So because it's a normal population, which means either it is directly a normal population, or even if it is from a non-normal population, the size of the sample is large enough that I can approximate it to a normal population. And let's say I know the variance of that population sigma squared. In that case, the critical region for me, going with that likelihood ratio test, the critical region is modulus of z greater than or equal to z alpha by 2 in case of a two-tailed test. Z is greater than or equal to z alpha when my alternate hypothesis is mu greater than mu naught, and z less than or equal to minus z alpha when my alternate hypothesis is mu less than mu naught. And here the test statistic that I am using, if the data is coming from normal, if the data is coming from a normal population, then the test statistic that is more appropriate for doing the testing of means is z equal to x bar minus mu by sigma by root n. Now this value we will compute, and we will see if the modulus of this z is greater than or equal to z alpha by 2 in case of two-tailed distribution, or it is greater than or equal to z alpha in case of the one-tailed test for greater than, and less than or equal to minus z alpha in case it's a one-tailed test for less than. Let's take a quick example to compute it. Suppose that it is known from the experience that the standard deviation of the weight of 8-ounce package of cookies made by a certain bakery is 0.16 ounce. Right? So we are setting the standard deviation, we are specifying the standard deviation sigma as 0.16. Alright. To check whether its production is under control on a given day, to check whether the true average weight of the package is 8 ounces. So my mu naught, I am setting it as 8 because I want to check it whether it is 8 ounce or not. Employees selected a random sample of 25 packages. Okay, n is 25, and find that their mean weight x bar, because it's a sample, it is x bar. X bar is 8.091. Okay. Check since the bakery stands to lose money when mu is greater than 8 and customer loses out when mu is less than 8. So I don't want mu to be greater than 8. I don't want mu to be less than 8. So that is where I want to test the null hypothesis of mu equal to 8 against the alternate hypothesis of mu not equal to 8 and 0.01 level of significance. So I want to find my, I am having my alpha as 0.01. Now I have a two-tailed kind of a test. So based on this, I can find out Z alpha by 2, right? Because that is the one that I have to compare with. Alpha by 2 will be 0.005. So I'll take in Excel, I'll take the absolute value. So I'll take it as norms inverse 0.005. So my Z alpha by 2 is 2.57. So what is that I want now? Whatever is my mod Z value that I am computing. Now let me compute my Z value also. Right? What is the Z value that comes out? X bar minus mu divided by sigma by root n. Sigma by square root of n. But of course here I am making an assumption that the population is a normal population, right? Because it's not that large enough. So I am saying I am making an assumption that the population is a normal population. Z is 2.84. So this Z is 2.84, which is greater than the Z alpha by 2, which is 2.57. So if the mod Z, if I am looking at my critical region, the mod Z greater than or equal to Z alpha by 2. Yes, it is greater than. So my value is in the critical region. So I have to reject the null hypothesis. And I am rejecting the null hypothesis. So which means my production process need to be altered. The mean weight is not coming out to be 8. It is much higher than 8. So there is a difference. Mu is not equal to 8. Mu is, in this case, mu is much higher than 8. And if I want to find out what is the p-value for this, I can directly look at corresponding to this 2.84, what is the area under the normal distribution curve. Whereas here I can do it as norms dist. I'll take my Z value as 2.84, which will give me that the alpha. This is 1 minus alpha. So I'll take it as 1 minus of this, which will give me my alpha. The alpha in this case this is the Z value is 2.84, right? So let's understand here. The Z value is 2.84. So I am finding out this whole area in Excel, which is coming. This area is alpha by 2. This area is alpha by 2. So this whole area is 1 minus alpha by 2. Right? This whole area, whatever I have got by using the norms dist, is 1 minus alpha by 2. So 1 minus alpha by 2 or 1 minus p value by 2 is this much. So based on this, I can find out the p value. So p value by 2 is this much. So I can very well take it as 2 times 1 minus of this will come out as my p value. The p value is 0.4%. So in this case, the p value is 0.446%, which is much lesser than 0.05, because we will compare the p value, or let me take it in numbers itself. We'll take the p value, we'll compare it with your alpha. Alpha is 0.01. P value is less than alpha, so we are rejecting the null hypothesis. We are taking the decision in favor of the alternate hypothesis. That is how we solve the decision problems using this p value and using this critical region as well. So we need to be comfortable with both the mechanisms. Now, when we are dealing with the large samples, size greater than 30, from a population that is not necessarily normal but having a finite variance. So if the variance is more or less finite but the sample size is too large but the population need not be normal, I can very well use the central limit theorem to justify the test for normal populations. And even when the sigma, so if the population is normal, I can directly use my z test for comparing, for finding out, for testing for the mean. But if the population is non-normal, right, as long as the sample size is greater than or equal to 30, I can still go ahead, use the central limit theorem, and I can justify the population to be normal, especially if the sigma squared is known. But if the sigma squared is also not known, but still the population size is greater than 30, the sample size is greater than 30, then I can very well use S squared, which is a representative of the sigma squared, for computing my test statistic. So in all these cases, as long as the sample size is large enough, I can very well use the normal distribution, the Z test and Z alpha by 2 as the critical region definition, as long as my sample size is much large enough so that I can make the approximation to a normal distribution even if the populations are non-normal. So we can look at the example regarding the same. Suppose that 100 high performance tires, so N is 100 here, 100 high performance tires made by a certain manufacturer lasted on an average 21,819 miles, right? So I'll have my X bar 21,819 miles with a standard deviation. Now here I don't have the population standard deviation, right? We are trying to find out the population standard deviation from the sample itself, the S, 1295 miles. But the sample size is large enough, so I can make an approximation to a normal distribution. Now I am making a null hypothesis, mu equal to 22,000. So my mu naught, which is 22,000, I am trying to look at against an alternate hypothesis, mu less than 22,000. Right? I am only seeing that the tires will perform less than 22,000. The tires will run for less than 22,000 kilometers. So anything more than, greater than or equal to 22,000, it's not in my rejection zone. Only the mu is less than 22,000 is in my rejection zone. Now because of this, what I really want is, it's a one-tail test, right? Because my alternate hypothesis is only in the lower zone. So I require it as one-tail test, and it is that too on a less than side. And the alpha value that we are setting is 0.05. And this whole 0.05 should be on one side, the lower side itself, right? So this is where my critical region will come out as the Z value, right? This is where if I look at the critical region, the Z value should be less than or equal to minus Z alpha, right? So the Z value that we are computing, it should be less than or equal to minus Z alpha. So let me compute my Z alpha here. I'll take the absolute value of norms inverse corresponding to alpha is 0.05. All the alpha should be on one side, so it is 1.64. So I can take the negative of Z alpha, which is nothing but the minus of this value, minus 1.645. Now I have to find out my Z value, which is the mean X bar, which is X bar minus mu divided by sigma by root n. Sigma is, I am taking S only, S by root n, square root of 100, which is giving me my Z value is minus 1.39. Now you could see that the Z value minus 1.39 is greater than the minus Z alpha, which is minus 1.64. But it will be in the rejection region only if it is lesser. So here it is not falling in the rejection region. Minus 1.39 is greater than minus 1.64. So I cannot reject the null hypothesis here. So which means when I am making a conclusion, I'll say that there is no evidence which is very significant that the tires are not as good as assumed under the null hypothesis. Under the null hypothesis, we have assumed that the tires have 22,000 miles. Now, what this is also saying is it's not that drastically, significantly lesser than this 22,000. So there is no convincing evidence for me to reject the null hypothesis. I can very well go ahead with the acceptance of the null hypothesis itself. So, and if I have to compute the p-value here, again, this whatever, now I will try to look at my z value on the standard normal distribution table. So I'll use it as norms dist, this particular z value. So which is coming out as 8.1%. So if it is 8.1%, if the alpha is set at 8.1% instead of 5%, then I would have rejected the null hypothesis. So the p-value is p-value is 0.08, which is greater than my alpha value, which is 0.05. That's where I will not be able to reject my null hypothesis. I'll have to take my decision in favor of the null hypothesis itself. So either I can use the p-value scenario for doing the comparisons or for accepting or rejecting the null hypothesis, or I can very well find out the critical region and see whether my computed test statistic is within the critical region or within the acceptance region. Fine? Alright. Then, the other scenario, the third scenario, the first scenario is the population is normal. I'll use Z. The second is population is non-normal, right? But the sample size is greater than or equal to 30, even if I don't know the sigma squared also. Then also I'll use Z. But on the other side, the population is non-normal, size is less than 30, sigma squared is also not known. Then, based on the likelihood ratio technique, what it says is x bar minus mu by s by root n. In this case, it will follow a t distribution. It will not follow a z distribution, standard normal distribution. It will not follow a standard normal distribution. Right, the same thing x bar minus mu by s by root n was following a standard normal distribution when your sample size is large enough. But when the sample size is not large enough, it does not follow a z distribution. It follows a t distribution with n minus 1 degrees of freedom, which means my critical region will come out as mod t greater than or equal to t alpha by 2 and with n minus 1 degrees of freedom in case of two-tailed test, or it is t is greater than t alpha with n minus 1 degrees of freedom in case of one-tailed test on the greater than side, or t less than or equal to t alpha n minus 1 degrees of freedom in case of the less than mu naught kind of alternate hypothesis. So let's take this example to really test it out. The specification for a certain kind of a ribbon call for a mean breaking strength of 185 pounds Okay, so in this case, my mu naught is 185 power. If 5 pieces randomly selected from different roles, now here the sample size is only 5. Having the breaking strength 171.6, now we are having the individual data 191.8, 178.3, 184.9 and 189.1. So these are the individual values that we have. Okay, test the null hypothesis mu equal to 185 against the alternate hypothesis mu less than 185, so which means it's a one-tailed test, so I have to compare with whether my t value is less than or equal to t alpha with n minus 1 degrees of freedom. So in this case the n minus 1 degrees of freedom is 4 degrees of freedom, right? N minus 1 degrees of freedom is 4 degrees of freedom. So first let me compute the mean, the x bar, which is the sample mean, which is nothing but the average of these numbers. I'll also compute the s, which is the sample standard deviation associated with these numbers. The sample standard deviation associated with these numbers is 8.2. So based on this, now I can find out my t value, which is nothing but x bar minus mu divided by sigma by root n, or s by square root of n. So my t value is minus 0.5. Fair enough. Now I have to also compute the t alpha. Now alpha value we have set it as 0.05. So I can find out t alpha. T alpha, I will get it as t inverse. I can look at into my t distribution table as well. My alpha is 0.05 and degrees of freedom is 4. In case of Excel, I have to take it as the double. So I'll take it as 0.1. So which will work out as 2.13. And because I want the negative side, I'll take, so I'm looking at less than t less than minus t alpha. So negative of t alpha, if I am looking at, which is nothing but minus of this one, okay, minus 2.13. Now I'm so my alpha value or my t value is minus 0.5. Right now my critical region is more like this, minus 2.13. Lesser than this minus 2.13 is the critical region, right? Lesser than minus 2.13 is the critical region. So whereas my t value minus 0.5 is somewhere here, so it is not in the critical region, so I would not be able to reject the null hypothesis. And same way, if I compute the p value here, right, the p value is nothing but I will find the t distribution of this particular x with respect to the degrees of freedom being 4, and I have it as a one-tailed distribution. In this case, the p value, I'll take the absolute of it. I'm getting a p value of 31.97%. So if the p value is, if the alpha is set as 31.97%, then there would have been a chance that the null hypothesis would have been rejected. So here we are very much making a conclusion that I cannot reject the null hypothesis, and we have to make our decision in favor of the alternate, in favor of the null hypothesis itself. So that's how I can do different kinds of tests relating to the means. Depending on whether the population is normal or the sample size is large enough, I would go with a Z test, or if my sample size is much smaller and even the data is not coming from, and I don't know the variance of the population, then if I have to compare the means, I would rely more and more on a t test rather than a Z test. Alright. Now looking at the tests that are concerning with the difference between the means. Now that we have looked at the test relating to the computation of the mean, we will look at those tests which are concerning the difference between the two means, mu1 minus mu2. Here also I can follow the same process. I can look at whether the population is normal or not. If it is normal, fair enough, I'll use the Z as my test statistic. If they are not normal, I'll see at least if the sample size is greater than or equal to 30. Then also I can do an approximation of normal and I can use a Z. And finally, if the sample size is less than 30. So all these processes remain the same for the testing of the means as well as the testing the differences between the means. So if you look at the first scenario, where I am talking about the independent random samples sizes n1, n2 coming from normal population, the means mu1 and mu2, their variances are known, sigma 1 squared and sigma 2 squared. In that case, I am trying to find out the null hypothesis, which is regarding the difference between the means, is some constant. So this is my null hypothesis here, and I am trying to test it against an alternate hypothesis. It could be a two-sided alternate hypothesis saying mu1 minus mu2 is not equal to delta. That's a two-sided alternate hypothesis. Or I could have had mu1 minus mu2 less than delta. It's a one-side alternate hypothesis. Or it could be greater than delta, even that is a one-side alternate hypothesis. So because it's a normal distribution, I can use the Z test. The critical region is mod Z is greater than or equal to Z alpha by 2. In case of a two-tailed test, Z is greater than or equal to Z alpha. In case of one-sided, Z less than or equal to minus Z alpha in case of one-tailed test, which is on the less than side. But the only difference being my Z computation will differ. In case of testing of the means, we have computed the Z as x bar minus mu divided by sigma by root n. Now understand here, x bar is the sample mean. Now here our sample mean is x1 bar minus x2 bar, the difference, minus mu. Mu was the hypothesized mean, population mean. Now here I will take it as delta, the hypothesized difference, divided by sigma. There it was only the standard deviation because it's only one single sample that is existing. Now I have two samples. So if I want to find out the standard deviation of it, it is nothing but first I have to compute the variance, sigma 1 squared by n1 plus the sigma 2 squared by n2. The variances can be added. The square root of that will become my standard deviation. So sigma by root n will get translated into square root of sigma 1 squared by n1 plus sigma 2 squared by n2. So this is what will be my Z value. I'll try to see, depending on whether my alternate hypothesis is a two-tailed or one-tailed, I'll use these as my critical regions for whether to accept the null hypothesis or reject the null hypothesis. The same fundamental I have to use when we are dealing with independent random samples coming from non-normal populations also, or even if they are having unknown variances also, but as long as the sample size is large enough. The sample size is large enough so that the central limit theorem can be applied, wherein I can approximate it to a normal distribution, but by substituting S1 for sigma 1, S2 for sigma 2, which are the sample standard deviations of each of the samples, I can substitute them to be their population standard deviations, and I can very well use the same test statistic for testing the difference between the means, as long as the sample size is large enough. Now, if you look at this scenario here, take a simple example. I'm conducting an experiment, right? In this case, I'm conducting an experiment to determine whether the average nicotine content of one kind of cigarette exceeds that of the other by 0.2 milligrams. So we want to find whether mu1 minus mu2 equal to 0.2. So at least some of the information that I have, the delta value in this case is 0.2. Okay. If n equal to 50 cigarettes of the first kind, so n1 is 50, have an average nicotine content of x1 bar is 2.61. x1 bar is 2.61. Okay. And the standard deviation S1 is 0.12 milligram. Okay. Whereas N2 equal to 40 cigarettes of the other kind have an average nicotine X2 bar is 2.38 with a standard deviation S2 is 0.14. Test the null hypothesis mu1 minus mu2 equal to 0.2 against an alternate hypothesis mu1 minus mu2 not equal to 0.2. So immediately we are looking at a two-tailed test. So my critical region is mod z greater than or equal to z alpha by 2. So I have to compute my z alpha by 2. So the alpha is being given as 0.05, which means alpha by 2 is nothing but 0.025. Base the decision on the p-value corresponding to the appropriate test statistic. Now here I can very well, my null hypothesis is mu1 minus mu2 equal to 0.2. Alternate hypothesis is mu1 minus mu2 is not equal to 0.2. And I am specifying my level of significance alpha, which is 0.05. Now I have to compute my test statistic, right? The test statistic is x1 bar minus x2 bar minus delta divided by square root of sigma 1 squared by n1 plus sigma 2 squared by n2. So I can find out my test statistic z, which is working out as x1 bar minus x2 bar minus delta divided by square root of sigma 1 squared by n1, sigma 1 squared by n1 plus sigma 2 squared, which is s2 squared by n2. So this is what is working out as the test statistic, which has worked out as 1.075 for us. Then it is being asked that I have to find this decision based on the p-value. So I have to compute the p-value corresponding to this. So I'll look out into the z tables for the corresponding p-value. I'll look at it under this particular area. wherein I can compute the p-value. If I'm going with the tables, I'll look out for 1.07, and because it's a two-tailed test, I'll multiply it with 2. Whereas here in Excel, corresponding to this 1.07, this is the area, right? So my 1.07, this is 0, 1.07 is this one. So when I'm saying a norms disk function, I'll get this as the area, right? But if I want the p-value, I want to get this area into 2. So I will take it as 1 minus whatever I get through norms list, and I'll do the double of it. That is what will give me the p-value. So I'll take it as double of 1 minus of the norms dist function associated with this z value. In this case, it is working out to around 28%, right? The 2.2821. So this is the p-value. P-value is greater than the significance level alpha, 0.05. Even if I have to compute my critical region here, I have to look at it with respect to z alpha by 2. So I'll use the norms inverse associated with z alpha by 2.025. So z alpha by 2 is 1.95. I'm computing my z, which is 1.07. So 1 mod 1.07, I'll say, is it greater than or equal to 1.95 or 1.96? If it is greater than or equal to, then it is in the critical region. I'll reject it, but it is not. So I'll not be able to reject the null hypothesis going with the critical region method. Even going with the p-value method, p-value is 0.28 greater than 0.05. So I would not be rejecting the null hypothesis. So we say the difference, whatever has come out from the means, with this sample the difference is 0.23. It's not that significantly different from 0.2, right? So the differences the small difference that has really come out is very much attributed to chance. So I can very well say that I can very well accept the null hypothesis, and I say that the difference between the nicotine content in both is approximately equal to 0.2 milligrams itself. So that is the way out. We are doing the testing and making inferences regarding the differences between the mean, provided my data is normal or the sample is large enough to approximate it to normal. But if the samples are much small, much less than 30, and sigma 1 and sigma 2 are also an unknown kind of entities, but if they are two random samples from two normal populations, and if they have the same variance, which is not known, but it is known that their variances are the same, in that case we have another statistic to work out, which is again x1 bar minus x2 bar minus sigma minus delta. Instead of putting sigma 1 squared by n1 plus sigma 2 squared by n2, we are pooling the variances, saying the combined variance is n1 minus 1 s1 squared. This is purely based on your chi-square distribution, right? If x1, x2, x3 are following a normal distribution, and x1 squared, x2 squared, x3 squared will follow a chi-square distribution, and their summation will follow again a chi-square distribution with nu1 plus nu2, the degrees of freedom also simply getting summed up. The same logic is being applied out here. The pooled variance is nothing but n1 minus 1, which is the degrees of freedom with respect to the first one, times s1 squared, n2 minus 1 s2 squared divided by n1 plus n2 minus 2. That is what we are calling as SP, which is the pooled standard deviation, into square root of 1 by n1 plus 1 by n2. So this one is following a t distribution with n1 plus n2 minus 2 degrees of freedom. So especially if you are having populations n1, n2, if you are having your populations where the samples are pulled out, where the sample size is much smaller, even the population variance is also not known, but it is known that the populations are coming, that the samples are coming from independent random samples are coming from normal populations whose variances are not known, but at least known that they are equal. Then the likelihood ratio test says that this particular statistic, the difference between the sample means and the hypothesized difference divided by the pooled standard deviation times square root of 1 by n1 plus 1 by n2 will follow a t distribution with n1 plus n2 minus 2 degrees of freedom. So if I have to test the mu1 minus mu2 equal to delta, in this case the critical region of size alpha is nothing but mod t greater than or equal to t alpha by 2 with n1 plus n2 minus 2 degrees of freedom. In case of two-tailed test, t greater than or equal to t alpha with n1 plus n2 minus 2 degrees of freedom for a greater than test, t less than minus t alpha times n1 plus n2 minus 2 in case of a less than one tail test. So we can very well try looking at an example to solve this again. In comparison of two kinds of paints, a consumer testing service finds that 4 1 gallon cans, right? So N1 is 4 1 gallon cans of one brand cover on the average 546 square feet. So X1 bar is 546 square feet with a standard deviation of 31 square feet. Then whereas 4 1 gallon cans of the other, N2 is also 4, on an average 492 square feet. Okay, X2 bar is 492 with a standard deviation of 26 square feet. Assuming that the two populations are sampled are normal, have equal variances, so I can very well use the pooled variances kind of a concept. Test the null hypothesis mu1 minus mu2 equal to 0. So which means delta I am taking it as 0. Against the alternate hypothesis mu1 minus mu2 is greater than 0. So I am looking at only a one tail test. So alpha is 0.05. So I don't need alpha by 2 here. Right? I don't need to compute alpha by 2. So my null hypothesis is stated as mu1 minus mu2 equal to 0. Alternate hypothesis is stated as mu1 minus mu2 greater than 0. The alpha is set as 0.05. So I have to compute my t value right now, right, corresponding to the 0.05. So I'll find out the critical region, which is my t value. I will find the t inverse associated with 0.05. So in case of Excel, I'll have to take it as 0.1 with the degrees of freedom n1 plus n2 minus 2. So I'll take it as 6 degrees of freedom, which is giving me 1.943. That's my critical region. So I will be rejecting this test if the t statistic that I am computing using this formula is greater than 1.943. If the t value that I am computing is greater than 1.943, then I would be rejecting the null hypothesis. So first let me compute pooled variance, which is nothing but n1 minus 1, n1 minus 1 s1 squared plus n2 minus 1 s2 squared, right, divided by n1 plus n2 minus 2, n1 plus n2 minus 2. So pooled variance is coming out to 818. So based on this, I'll compute my pooled SD, which is nothing but SP, which is the square root of the pooled variance, working out to 28.6. Now based on this, I can find out my test statistic, which is nothing but x1 bar minus x2 bar minus delta divided by pooled standard deviation into square root of 1 by n1 plus 1 by n2, 1 by n1 plus 1 by n2, working out to 2.66. So the test statistic is coming out to 2.66. It is much greater than 1.943. So I can very well reject the null hypothesis. I can very well conclude that the average of the first paint covers a much greater area compared to that of second. That's the kind of a conclusion that I can very well make. And in this case, if I have to compute my p-value, I can simply take it as the t distribution, wherein I am looking at my computed test statistic with 6 degrees of freedom going with a one-tailed test, which is telling me 1.8. If the p-value here is 1.8%, which is less than 5%, right? So that's where I have rejected my null hypothesis and taken the decision in favor of the alternate hypothesis. So this is the typical procedure that you employ if you have to compare the differences between the means between the two populations. And one more aspect is, these are all applicable when the two samples, right, n1 and n2, they are completely independent. If they are completely independent, then these are the procedures, these are the statistics that we are computing, etc. But if they are not independent, they are very much paired. Probably I am talking about before and after. Right? I am talking about a weight of a person before something is done, before a treatment is taken up, and after the treatment is taken up. They are not two independent populations altogether. It's the same population, but before a certain thing and after a certain thing. So this is where we cannot use the same test if the observations are very much paired. I cannot use this test. In this case, I have to first compute the difference, and those differences I need to treat them as the test concerning the means itself. So the differences I can take them as raw values and go with the z as x bar minus mu by sigma by root n. Or I could take it as t is x bar minus mu by s by root n. But this is the mechanism that we are going to adopt if we are talking of the differences between the two paired samples versus independent. If they are independent, this is what is the test statistic that is more appropriate for them. But if they are dependent, if they are paired, then I have to use the tests that are associated with the means to work out on these differences. So I have to go with these kind of test statistics, I have to go with the decision criteria based on these degrees of freedom in case of t n minus 1 degrees of freedom, rather than going with n1 plus n2 minus 2 degrees of freedom. So that's one more thing that we have to be comfortable with when we are working with two different populations which are not independent but which are paired, and I'm trying to compute or compare their means. Alright, so these are the different kinds of tests that are associated with comparison of the means of two different populations. Alright. Now that we are done with doing various statistical tests concerning the mean, we will move towards performing the statistical hypothesis tests associated with the variances. There are so many real world applications for the same, wherein I want to measure the volatility of a particular variable, or I want to see how a particular variable is consistent across the two different groups of data. So there are various such kind of applications, and you could see in some of the cases when we have tested the means also earlier, we have made an assumption that the variances are equal. So there is some kind of a necessity that is coming out that the variances between the groups are more or less equal. So we are executing different kinds of tests where the variances will form an important aspect of them. If you see some of the null hypothesis that we can bring out in this regard, we say the variance of a normal population is equal to a particular constant. So variance equal to 0.5. So this could be one kind of test that we would be interested in. Or in this case, the likelihood ratio of the equality of the variances of two normal populations, sigma 1 squared by sigma 2 squared. Comparing the two normal populations, whether sigma 1 squared is equal to sigma 2 squared or sigma 1 squared is some multiple of sigma 2 squared, some such kind of comparisons also I may be interested in making. So in all these cases, we are primarily looking at the tests associated with the variance. I'm looking at a random sample of size n, normal population. So the first of it, I'm trying to see the null hypothesis works out as sigma squared is some constant. And I have a two-sided alternate hypothesis which says sigma squared is not equal to sigma naught squared. Or I also have one-sided alternative saying sigma squared is greater than sigma naught squared, or sigma squared is less than sigma naught squared. These are all my alternate hypotheses. Now, when we are working out with a likelihood ratio technique, what is this likelihood ratio technique? We will reiterate what we have discussed in our previous session. When I am keeping my alpha value as constant, that particular test statistic which will try to minimize the beta error, that is what we are calling as the likelihood ratio technique. So we are seeing that the likelihood ratio technique is giving me a test statistic that is based on S squared, which is the sample variance, and the critical regions in this case are coming out to be chi-squared value greater than or equal to chi-squared alpha, whatever is my test statistic, greater than or equal to chi-squared alpha with n minus 1 degrees of freedom. If I am going with a one-sided alternative, so it's a greater than alternative. If I am going with, I will have to test the chi-squared value which is computed. This is the test statistic. The test statistic is greater than or equal to the critical region value chi-squared at alpha significance level and n minus 1 degrees of freedom. If I am looking at for a less than kind of alternate hypothesis, sigma squared less than sigma naught squared, then I will compute a chi-squared value and check it whether it is less than chi squared with 1 minus alpha significance level and n minus 1 degrees of freedom. And the chi squared that we are computing, the test statistic that we are computing in this regard is n minus 1 s squared by sigma naught squared. So n minus 1 is the sample size, s squared is the variance that you are computing based on the sample, sigma naught squared is the variance that you are hypothesizing for this particular data. And when you are moving slightly forward to understand the critical region for two-sided test, then we are rejecting the null hypothesis if the chi-squared is either greater than the chi-squared alpha n minus 1, or is it if it is less than if the chi-squared is less than chi-squared 1 minus alpha by 2 with n minus 1 degrees of freedom, because we need alpha by 2 area on both the sides. So we'll reject it if it is greater than chi-squared alpha by 2 with n minus 1 degrees of freedom, or it is less than or equal to chi-squared 1 minus alpha by 2 with n minus 1 degrees of freedom. That's the way we define our critical region with respect to the tests that are associated with the variances. Let's look at a quick example to simplify this. Suppose that the uniformity of thickness of a part used in a semiconductor is critical. Uniformity of thickness, which means it's a consistency that I am more interested in. Measurement of the thickness of a random sample of 18 such parts. So my n is 18. Have a variance, sample variance, s squared is 0.68, where the measurements are in thousands of an inch. Fair enough. The process is considered to be under control if the variance of thickness is given by the variance not greater than 0.36. So I need my sigma naught squared. Sigma naught squared, I am taking it as 0.36. And it is a one-tailed test now, because we are talking about it should not be greater than 0.36. So my rejection zone is so the rejection zone is sigma squared greater than 0.36. So I have to compute the chi-squared value accordingly. Chi-squared is nothing but n minus 1 s squared by sigma naught squared. So I can very well find out what should be the value at which the rejection or acceptance has to happen. Assume that the measurements constitute a random sample from normal population. Test the null hypothesis, sigma squared is 0.36. Again, the alternate hypothesis, sigma squared is greater than 0.36 at an alpha of 0.05. So here my critical region is chi squared is greater than or equal to chi squared alpha n minus 1. So let me compute my critical region now that I have already defined my null hypothesis. Step 1 is I am defining my null hypothesis, chi squared equal to sigma squared equal to 0.36. The alternate hypothesis is sigma squared greater than 0.36. I have defined the significance level 0.05. Now I need the rejection zone. My chi squared should be greater than, I need to find the critical region. So this is where I am finding out my critical region, the chi squared inverse function. I am going with the probability of 0.05. Right here I have to take the other way. I'll have to take it as 0.95, and the degrees of freedom is n minus 1, which is with 17. So 27.58 is the critical region that is associated. So which means if I am getting my test statistic computed value chi squared is greater than or equal to 27.587, I will be rejecting this null hypothesis, otherwise I will not be. Now from here I can very well find out my chi squared test statistic value. Test statistic is the chi squared value that I am talking of, n1 minus n minus 1, 18 minus 1 S squared divided by sigma naught squared. So this is 32, right? So chi-squared value is 32, greater than or equal to 27.58. So I am rejecting the null hypothesis and taking my decision in favor of the alternate hypothesis. So my alternate hypothesis here is the variance is greater than 0.36. So the process is not under control. So some kind of mechanisms or some kind of workout I have to do to bring the process into control. That's how I can do my test regarding the variances of the data. Now, if I am in some cases, I will not be comparing the variance with a constant like this, right? I will not be checking whether the variance is equal to a particular constant or not. I am more or less checking the equality of the variances of two different populations, right? Instead of looking at saying is the variance equal to something, some value or not, here I would be more concerned by looking at is the ratio of the variance or the equality of the variances of two groups of population. That is what I would like to compare, and for that I'll take two different samples or from these two different populations, and I'll try to do the comparison of the sample variances. Based on the comparison of the sample variances, I want to really make a conclusion regarding the population variance. Look at the scenario. I'm talking of S1 squared and S2 squared being the variances of independent random samples of size N1 and N2. Normal population, their variances are sigma 1 squared and sigma 2 squared. We have already discussed earlier the ratio of their sample variances divided by their population variances. They will follow a F distribution. So when we talked about the F distribution, we talked about this. S1 squared by sigma 1 squared divided by S2 squared by sigma 2 squared. It is going to follow a normal, it is going to follow an F distribution. So we could very well say sigma 2 squared, just rearranging it, sigma 2 squared S1 squared by sigma 1 squared S2 squared is a random variable having an F distribution with N1 minus 1 degrees of freedom and N2 minus 1 degrees of freedom. So based on this, we'll compute our test statistic. Here the test statistic is S1 squared by S2 squared. I'll check whether this test statistic is greater than or equal to the F value, which is nothing but F that is computed at alpha significance level, N1 minus 1 degrees of freedom and N2 minus 1 degrees of freedom. Or if I am doing S2 squared by S1 squared, in that case I'll look at it as F alpha, again N2 minus 1 degrees of freedom, N1 minus 1 degrees of freedom. So this is how we work out with the one-sided alternatives. Whereas when we are looking at two-sided alternatives, right, I would simply look at S1 squared by S2 squared. If it is greater than F alpha by 2, N1 minus 1, N2 minus 1, or is it greater than or equal to F alpha by 2, N2 minus 1, N1 minus 1 if N1 S1 squared is less than S2 squared. And this test is always based on the right hand side tail only of the F distribution. Because if we have an equality here, right? If x is a random variable, it has an F distribution with nu1 and nu2 degrees of freedom. Then we can simply say 1 by x is also having an F distribution but reversal, be it nu2 and nu1 degrees of freedom. So that's the reason when I am taking S1 squared by S2 squared, if S1 squared is greater than S2 squared, I'll take it as S1 squared divided by S2 squared. I'll compare it if it is greater than or equal to F alpha by 2, N1 minus 1, N2 minus 1. If S2 squared is greater than S1 squared, I'll simply take it as if that ratio is greater than or equal to f alpha by 2 n2 minus 1 n1 minus 1. That's the way we can quickly check and say whether the variances across the groups of data are more or less uniform or they are differing drastically. Now, taking a quick example to understand the same, I am comparing the variability of the tensile strength of two kinds of structural steel. An experiment yielded the following results. Okay, N1 is 13. We have taken a sample size of 13. S1 squared is 19.2. N2 is 16. S2 squared is 3.5, where the units of measurement are 1000 pounds per square inch, whatever it is. Assuming the measurements constitute independent random samples from two normal populations, test the null hypothesis sigma 1 squared equal to sigma 2 squared against the alternate hypothesis sigma 1 squared not equal to sigma 2 squared. So this is the two-tailed test. Null hypothesis is sigma 1 squared equal to sigma 2 squared. Alternate hypothesis is sigma 1 squared not equal to sigma 2 squared. The alpha I am setting it as 0.02. So here I require alpha by 2. Right, I'll take it as alpha by 2, which is nothing but this number by 2.01. So here S1 squared is greater than S2 squared. Right, from the sample I can see that S1 squared is greater than S2 squared. Because of this region, I'll take the ratio S1 squared by S2 squared. It is greater than or equal to F alpha by 2 N1 minus 1 N2 minus 1. So let me find out that critical region. The critical region is F alpha by 2, so I'll use it as F inverse function. Alpha by 2 is 0.01. Right, N1 minus 1. 13 minus 1 comma n2 minus 1 16 minus 1, so which is working out to 3.666. so if my s1 squared by s2 squared is greater than 3.666, I will reject the null hypothesis. Now let me find out the ratio s1 squared by s2 squared. S1 squared divided by S2 squared is coming out to 5.48, which is greater than 3.666. So the null hypothesis is rejecting. So we could very clearly say that sigma 1 squared is much higher compared to that of sigma 2 squared. So the variability of the tensile strength of the two kinds of steels that I am looking at, they are not consistent. There is a significant difference that is existing between the two groups. So that's how different kinds of numericals can very well be taken to understand different hypothesis tests that are associated with comparing the variance to a particular constant, or even the comparison between the variances of two different groups. Alright. Now, the next topic that I am going to look at in this context is the test that is associated with the proportion. Now that we are already comfortable doing the test with respect to the means, right, mu equal to mu naught kind of test, mu1 minus mu naught equal to delta kind of test, and even the variances sigma squared equal to sigma naught squared, or we have also looked at sigma 1 squared by sigma 2 squared kind of tests. So there are different kinds of tests which we have looked at regarding the means as well as the variances. Now I want to go to the next aspect where we are looking at the tests which are associated with the proportion. So generally for analyzing the count related data, so count is what will be related to proportions, because the count of something divided by the total is your proportion. Generally, to analyze your count data, we may use some binomial distribution or a Poisson distribution in some cases, and or in some other cases we may use some other discrete kind of distribution. But the most commonly used distributions for counting related variables is my binomial or Poisson or any other discrete distribution. So that's where, when my objective is to make some kind of inferences regarding the proportions, I'm more interested in a hypothesis like this: theta equal to theta naught. I'm generally looking at it as a binomial distribution. Theta is the probability or the proportion that is associated, the probability of success that is associated with a binomial distribution. And if it is a one-sided alternative, I'll look at it as theta is greater than theta naught. And based on that, we look at if the size of the critical region is alpha, I'm looking at the value of x greater than k alpha. K alpha is that smallest integer for which the overall, the summation of all the binomially distributed probabilities is lesser than or equal to that particular value. So less than or equal to alpha. I am looking at that particular summation. So if we say uh, we are talking about a test being performed, a trial, 10 trials are being 10 trials are being conducted. So there is a chance of getting 0 successes, 1 success, 2 success, and even up to 10 successes. So I am looking at, out of n trials that I have performed, I am seeing for each of the success what is the probability. I'll sum up all these probabilities in such a way that this summation is less than or equal to that particular alpha. So if this sum of only 0 is still less than 0.05, I'll look at this also. If the sum of these two is still less than 0.05, I'll include this also. The sum of these three probabilities is greater than 0.05, then I'll say I'll stick out to this, because it's the maximum value. It's the maximum value where my summation is lesser than or equal to alpha. So we are looking at critical region computation first. What is that particular k alpha value? It's the smallest integer for which this whole thing is less than or equal to alpha. And in some cases we can even test the two-tailed alternative, wherein I am looking at x greater than or equal to k alpha by 2. K alpha is the same kind of a definition that I am giving. Right, I'll go with k alpha being the same, the alpha being the same as defined, and similarly I can also look at k dash alpha by 2. X is less than or equal to k dash alpha by 2. X is greater than or equal to k alpha by 2. So that's the typical computation of the range or the critical region we will do, and based on that we can make our conclusions regarding inferences regarding the population theta value. Let's take a simple example. If x equal to 4 of n equal to 20, let me take a very simple example. X is equal to 4, n equal to 20. Patient suffered serious side effects from a new medication. The test the null hypothesis theta equal to 0.5. So our null hypothesis is theta equal to 0.5 against an alternate hypothesis theta not equal to 0.5, and the alpha value we have set it as 0.05. So theta is the true proportion of the patients suffering serious side effects for the new medication. Now I have to find out the test statistic, which is the observed number of successes. So we have got the observed number of successes, x is 4. Okay. Now I have to find what is the probability that x is less than or equal to 4. I have to find what is the probability that x is less than or equal to 4, because I'm trying to look at the test which is greater than, which is not equal to 0.5. So I will look at the probability of x less than or equal to 4. So which means I want to check the probability of x is 0, x is 1, x is 2, x is 3, x is 4. So I can very well use NCX. So NCX is 0 multiplied by theta to the power x, theta is 0.5 to the power x multiplied by 1 minus theta 0.5 to the power n minus x, which is 20 minus x. So the probability that x is less than or equal to 4 is, I'll get the probability x is less than or equal to 4 is the summation of all these things, which is working out as 0.0059. So this is the probability that x is less than or equal to 4. And if I want to find out my p-value, I'll take the double of it. So the p-value computation in this case will become twice of this, which is around 1.18%. 1.18% is less than my significance level, which is 0.05. And because of that reason, I can very well, because it said two-tailed test, first I am finding out the probability value of one tail, and then trying to double it to get the two-tailed value, which is working out to 1.18% less than 0.05. So I will reject the null hypothesis, and I can very well conclude that theta cannot be equal to 0.5. Theta is very much, in this case I could see that it is 4 by 20, so which is around 0.2. So theta cannot be a 0.5, it's very much away from 0.5. So this kind of a mechanism I can follow when I am doing a binomial distribution based test for proportions. For smaller values of n, there are tables associated with the binomial probability distribution and the binomial tables. But if the n values are going larger and larger, then I cannot use the binomial tables. Rather, I can very well use the binomial approximation to the normal approximation to the binomial distribution. We know that the binomial distribution has a mean of n theta and a variance of n theta into 1 minus n theta, 1 minus theta. The same logic I can put into my formula as well. Z is x minus mu by sigma. So wherein I can take x minus mu divided by square root of n theta into 1 minus theta. So this follows a standard normal distribution, which means the mean is 0, variance is 1. So I can very well test the null hypothesis of theta equal to theta 0, theta naught against the alternatives going with this normal distribution kind of an approximation. So if I am going with a two-tailed test, I'll look at it as mod z greater than or equal to z alpha by 2. If I'm going with a one-tailed test, I'll look at z greater than or equal to z alpha or z less than or equal to minus z alpha. And in some cases, I would also prefer going with a continuity correction as well. Instead of taking the x as it is, I'll take it as x plus or minus 1 by 2. This is what we are calling as a continuity correction. Right? We have checked it earlier. Instead of directly taking the x, because we are approximating this to a normal distribution. So, if I say x is equal to 6, x can't be equal to 6. So I will try to include it as from minus 5.5 from 5.5 and above. So this is where in some cases I do a minus half, in some cases I'll do a plus half. So when my part is saying when I have to look at theta greater than theta naught, then the x I will take it as x minus 1 by 2. Right? So we use the minus sign when x is exceeding the n theta naught, and when x is lesser than n theta naught, I'll look at it as x plus 1 by 2. So these are some of the adjustments also we will make before we really solve some kind of simplification and make conclusions regarding the proportion. So just looking at one small example regarding the same, an oil company claims that less than 20% of all car owners have not tried its gasoline. So theta we are talking about as zero point 0.2 or 20%. Test this claim at 0.01 level of significance. If a random check reveals theta cap is 22 out of 200, car owners have not tried the oil company's gasoline. Okay, so we are talking about the theta, which is the claimed one, as 0.2, right? So the alternate hypothesis is theta is less than 0.2, not that less than 20% of all the car owners have not tried. So that's where we are looking at only a one tail kind of a test. The alpha I am setting it as 0.01. So because it is 0.01 and it's a one tail, right? So I am looking at Z alpha, which is associated with, so I am taking the absolute value, norms inverse associated with 0.01, which is 2.326. I will reject the null hypothesis if the Z value that I am computing is less than or equal to minus 2.326, right? So that is what we have to work with. So now from here I have to compute my Z value, which will work out as x minus n theta. So the x here is 22 minus n theta, which is nothing but 200 times theta. So x minus n theta divided by square root of n theta into 1 minus theta. N is 200, theta into 1 minus theta, which is making it that the Z value is minus 3.18. So if the Z value is less than minus 2.326, we are rejecting the null hypothesis. So here it is minus 3.18, so which is less than minus 2.326. So I can very well reject the null hypothesis. I can very well conclude that less than 20% of all the car owners, they did not try the gasoline of that particular company. So that's how we can make some kind of conclusions regarding the proportions within a particular data. Alright. Then, moving a little bit forward, trying to see the tests associated with differences among the k proportions. I am not just looking at theta equal to theta naught kind of stuff. I am looking at different proportions. So theta 1 equal to theta 2 equal to theta 3 kind of stuff. So I am trying to look at whether the observed differences among the sample proportions they are significant or they are not significant. So if you simply look at different observed values x1, x2, x3, xk, these are the proportions of k independent random variables x1, x2, xk. They are having a binomial distribution, parameters n1 theta 1, n2 theta 2, so on. Now if n is very large, I can very well approximate the binomial distribution to a normal distribution. So each one can be converted into an appropriate standard normal distribution, xi minus ni theta I divided by square root of ni theta I into 1 minus theta I. And we also know that if x1, x2, xn, they are all independent random variables having standard normal distributions. And if I am talking about a y, which is nothing but the sum of their xi squareds, this will have a chi-square distribution with 1 plus 1 plus 1, which is n degrees of freedom. So it's a chi-square distribution with n degrees of freedom, which means I can also look at it as xi minus ni theta whole squared divided by ni theta I into 1 minus theta I. This is having a chi-square distribution with k degrees of freedom. So that is how I can very well go ahead in terms of testing out among the differences that are existing among the different proportions. So if I want to test theta 1 equal to theta 2 so on theta k, which is equal to some particular value, right? If I say all these are equal to 0.2, then I can very well use this critical region saying the chi-squared, I will compute it like this: each individual minus each individual proposed value versus the sample observed value squared divided by ni theta I into 1 minus theta I, which is the summation of all their independent squares, which is what we are calling as a chi-squared, which will have a k degrees of freedom. So our critical region will be chi-squared greater than or equal to chi-squared with alpha and k degrees of freedom. So which would work out as xi minus ni theta whole squared. This is how I am computing my chi-squared. Xi minus ni theta I whole squared divided by ni theta naught into 1 minus theta naught, because all of them are equal to theta naught. But in case this theta naught is not specified, but only I want to test theta 1 equal to theta 2 equal to so on theta k, then I can come out with a pooled estimate of theta, wherein I sum up all the successes divided by all the number of trials. That is what we are calling as a pooled estimate theta cap. So instead of theta naught, I will substitute this theta cap, but because the estimated value is being used for the computation purposes, we will reduce the degree of freedom by 1. So instead of looking at k degrees of freedom, we will go with k minus 1 degrees of freedom for computation of the critical region. So these are some of the things that are very much important for us to understand, especially if I am looking at the differences among the various proportions of the data. So this is where the alternative formula for chi-square statistic comes into picture. You look at it like this. So out of a sample of n1, n2, n3, so on, nk, let's say the number of successes are x1, x2, so on, xk. So these will be the failures. So arrange your data in this way. So each cell value we call it as Fij, means ith row jth column. You take the cell frequencies x1, x2, so on, they are belonging to the ith row jth column. And from here you also compute the expected cell frequencies, which is nothing but ni times theta. So depending on whatever is the theta value that you are expecting, whatever the theta value that you are proposing, if you know the theta, otherwise you will take it as theta cap if you don't know the theta. But ni, which is the sample size, times theta naught for all the particular values of k. So that would be filled here, and ni times 1 minus theta naught will be filled here. So if I don't know theta naught, I will substitute it with a pooled estimate, and then I will compute it as Fij, which is the observed value, minus the expected value whole squared divided by the Eij, which is the expected value. Fij, which is the observed value, minus the expected value whole squared divided by expected value. I will add up across all the rows and columns. That's one more way where we are testing the differences among the k proportion. Probably it would be much more easier if you are taking the example. Determine on the basis of the sample data shown in the following table whether the true proportions of the shoppers favoring detergent A over detergent B is same in all the three cities, right? So I want to look at each of these numbers, right? So let me take the first set 232 and 168, 260 and 240, right? Where the 260 are the people who are favoring detergent A, 240 are people who are favoring detergent B. This is 197, this is 203. So these are all Fijs, right? These are all Fijs. But now I want to find out my expected values for each one, because here if I go systematically for this example, my null hypothesis is theta 1 equal to theta 2 equal to theta 3. Alternate will become at least one of them is different from the rest. The alpha that I am using is 0.05. So going with this, if I have to reject my null hypothesis, look at the critical region here. So I am computing this. So the critical region is chi squared is greater than or equal to chi squared alpha and k. So if my computed chi-squared value is greater than or equal to chi-squared with 0.05 and k in this case is 2, right? Chi-squared is coming out to be k because two independent columns is what I am typically looking at. So chi-squared with 2 degrees of freedom, because we are talking of 3 different rows of data. The degrees of freedom is becoming n minus 1, which is 2. And we have to go with the pooled estimate as well here. So first let me find out the chi-squared inverse value, which is based on the probability of 0.05. So in Excel I'll take it as 0.95 with 2 degrees of freedom, which will give me 5.99. Okay, so if chi-squared is greater than 5.99, then I can very well reject the null hypothesis. Fair enough. Now theta is not given, so I'll have to go with my pooled theta, right? Because theta naught is not given, so I'll go with the pooled theta here. So which will make it 232 x1 plus x2 plus x3, 232 plus 260 plus 197 divided by the total, right? So it's better that I compute total in one cell, which is this plus this is the total. All right, so the pooled theta I can now take it as x1 plus x2 plus x3 divided by total n1 plus n2 plus n3, which is giving me a pooled theta of 0.53. So based on that I can find out my expected values. So here my expected value is ni theta 1. So ni is 400 multiplied by theta. So here the expected value is this one. Here it is ni times theta. Here it is ni times theta. And here it is ni times 1 minus theta, right? So the ni is this much times 1 minus theta. And here it is ni times 1 minus theta. Here also it is ni times 1 minus theta. So this is one thing that we are getting. These are the expected frequencies for each of the cells. These are the actual frequencies for each of the cells. Now I want to compute observed minus expected whole squared divided by expected. Like that I want to compute for all of them and I want to add them up. So here it is, if I do for the first one, it's nothing but observed minus expected whole squared divided by expected. So this is what is the computation that I am doing for all 6 sets. And the summation of all of them is what is my chi-squared value that is computed. Computed chi-squared value is nothing but the summation of all these things. which is around 6.473. And if you see this is greater than my table value or the critical region, which is 5.99. So which means I can very well reject the null hypothesis and I can make my decision in favor of the alternate hypothesis. And in this case, my alternate hypothesis is there is a difference in the thetas across the groups. So the true proportions of the population who are preferring between detergent A and detergent B, that proportion is not uniform across the cities. There is some level of significant difference that is existing among the people who are favoring detergent A versus detergent B in each of the cities. Probably if you look at the proportions, here it is 232 by 400, almost 58% people are preferring detergent A, whereas here it is only 52%, and whereas here it is around 49%. So the difference is not more or less similar. There is some level of big difference that is coming out, and that is what is our test also typically showcasing. So this is a kind of an example which you can look at when our objective is to perform the test where you want to compare the proportions across the various groups of data, right? All right. Now that we are done with the tests associated with differences among the k different proportions, now we'll move to the next aspect wherein I am looking at an analysis of R by C table. So where there are n number of rows and C number of columns. So we have so many such kind of problems in the real world. Applications wise, there are two scenarios where I can apply this. One, I'm talking about samples from R multinomial population. Probably I'm taking a sample from city 1, city 2, city 3, city 4. So 4 different cities. So there are multinomial populations and each trial permitting C possible outcomes. So I'm looking at looking at performing trials from different populations, and based on these trials I am looking at different outcomes for each of these populations, and I am looking at filling an R by C kind of a table. So if theta ij is the probability of the jth outcome from the ith population, I really want to look at the null hypothesis whether all of them are equal or not, whether all of them are uniform or not. Theta I1 equal to theta 1j equal to theta 2j, so on, theta rj. Right? So we are more looking at R different multinomial populations here. I want to test that from R different multinomial populations, I am taking different samples and I really want to see if the proportions are more or less uniform across all the groups. Right? So that is one such kind of an application where I will be looking at an R by C table. Right? Probably if there are, instead of two categories like in the earlier example, let's say I am talking about city 1, city 2, city 3, city 4. Right? I am looking at number of them who are favoring brand A, number of them who are preferring brand B, number of them who are indifferent between brand A and brand B, which means not much of a difference. So in this case, it's not it's not yes no kind of scenario. We have multiple such kind of categories here, making it as a R by C table. So whenever we want to analyze this R by C table, we have a different way of testing it out, again using a chi-square test itself. Or in some cases we'll deal with one sample only, it's not multinomial samples, but the proportion we are trying to look at whether the proportions of different groups within that sample are more or less uniform, or the proportions are differing across the groups. So these are both of these are typical applications where you will use an R by C table. The second one is what we call as a contingency table, having R rows and C columns. Each row represents C values of a non-numerical variable, and each column represents R values of another non-numerical variable. So we can have something like a marital status on one side. Let's say I talk about single, married, widowed, divorced, and I can have gender male, female here. Now if I am putting the counting of the observations across all this is what we are calling as a 4 by 2 contingency table. I am having R rows, C columns. Each row represents C values of uh, the gender, C values of a non-numerical variable. So I am having within the singles, how many males are there, how many females are there. And every column I see males wise, how many singles, how many married, how many widowed, how many divorced are there. So that's the typical way we represent a contingency table. The entries are typically the count data. So these are all the counts. How many males, how many male singles are there, how many female singles are there. So it's a count data. Both the row and total columns, I don't know what could be the numbers here. Adding these two things will come out to be this, adding these two. So they may very much vary. And these are assembled for the purpose of testing whether the row variable and the column variable. So is there any kind of a dependency between gender and marital status? Right? When I look at the number of people in each of the groups, is it like the marital statuses, is it like the gender, males and females are uniform across all the marital statuses, or there is a bias? There are more number of males who are singles, but there are very less number of males who are widowed. Some such kind of differences do exist, or is it like more or less uniform across all the groups? So we are trying to compare row versus column, whether there is some kind of dependency between these two, or they are more or less independent. So here what we are trying to do is theta ij is the probability that an item will fall into the cell belonging to the ith row and the jth column. So if I am saying theta ij is the probability that an item will fall into the ith row and the jth column, and theta I is the probability that an item will fall into the ith row, which is the total, or it falls into single. Similarly, if I say theta dot j is the probability that an item will fall into the jth column. So male, probability that a selected person will be a male, probability a selected person will be a single, probability that a selected person will be male as well as single. Now if they are independent, I should get theta ij as nothing but theta I times theta j. Right? If this value is independent, I should get theta ij as nothing but theta I times theta j. Now this is what we are trying to test. So we are going with the cell frequencies. This is Fij, this is Fi dot, and this I am taking as F dot j, and the total I am taking as F. So based on this I can go with the computation theta ij. So theta ij is the probability that an item will fall into the cell belonging to the ith row jth column. Theta I is the probability that an item will fall into the ith row. Theta j is the probability that it will fall into the jth column. Based on that I can find out theta I is nothing but Fi divided by F, and theta j is nothing but F dot j divided by F. Now if they are independent, right, if they are independent, the expected value I should get as the probabilities multiplied by the total number. So which is Fi divided by F, Fj divided by F into F. So the expected frequency is Fi times Fj divided by F, which is what we are calling as expected frequency. We also have the observed frequencies. This is the expected frequency. Observed minus expected whole square divided by expected. Across all rows, across all columns, you are finding that out and you are summing them. And that sum is what will translate into a chi-square value. And you reject the null hypothesis if that value exceeds chi-squared alpha r minus 1 c minus 1, because this would be a chi-square distribution with r minus 1 c minus 1 degrees of freedom. So if your computed chi-square value is greater than the critical region value, which is chi-squared alpha with r minus 1 into c minus 1 degrees of freedom, then I can very well reject my null hypothesis and I can make my conclusion in favor of the alternate hypothesis. So you look at this example. We'll try to solve this example and say whether we should go with the null hypothesis or we can reject the null hypothesis. Alright, let me look at the data here. Interest in statistics, low, average and high. This is the interest levels in statistics. Then we are talking of ability in mathematics, right, which is also low, average, high. Okay, we have some numbers here: 63, 58, 14. Here we have 42, 61, 47 and 15, 31, 29. Right, these are the observed frequencies. Now, once I know that these are the observed frequencies, I have to compute. So here, to start with, what is my null hypothesis? The ability in mathematics and the interest in statistics are independent. So there is nothing like if you are if you have high ability in mathematics, you will have high interest in statistics. Or if you have low ability in mathematics, you have high interest in statistics. There is no relation between the ability in mathematics and interest in statistics. That is what is the null hypothesis. And the alternate hypothesis says no, that is not the case. There is some level of dependency or relationship between the ability in mathematics and the interest in statistics. And we have alpha value as 0.01. So let me take the alpha value as 0.01. So I have to reject the null hypothesis if chi-squared value that we are going, the test statistic value, is greater than or equal to the chi-squared which we are computing at 0.01 level of significance. The degrees of freedom is 3 minus 1 into 3 minus 1 at 4 degrees of freedom. So I can find out the critical region value, which is nothing but, I'll take the chi-squared inverse function, and because I require it at 0.01 in Excel, I'll take it as 0.99 with 4 degrees of chi-squared in, okay, instead of dot I have to put it as comma. Okay, so 13.27 is the critical region value. So if my chi-squared, if the test statistic that I am computing is greater than or equal to 13.2767, then I am rejecting the null hypothesis. So I have to compute my chi-squared value. For that I have the observed frequencies, but I require my expected frequencies also. So to compute the expected frequencies, I require the totals across. So let me compute the total here, which is Fi 120, right? F of average is 150, F of high is 90. Similarly, here also I have to compute the sum. So here Fj is 135 here, then again 150 here, 75 here. And the total, which is F, is nothing but the summation of all these things, which is working out to 360. So now I can very well make out my expected frequencies for each of the groups. So this will come out as Fi multiplied by Fj divided by Fij, or probably F. That is the expected frequency of this group here. Similarly, for this group, if I want Fi multiplied by Fj divided by Fij, where Fi, yeah, F altogether, 25. So similarly here, Fi multiplied by Fj divided by overall F, 25. So this is my expected values. Similarly, right, I can compute, here it is, what is the value? Fi multiplied by Fj divided by total F. This is 50, sorry. So here again, Fi multiplied by Fj divided by F, 56.25. Here it comes out as Fi multiplied by Fj divided by F, 62.5. Fi multiplied by Fj divided by F, which is 31.25. Now here Fi multiplied by Fj divided by F, making it 33.75. Fi multiplied by Fj divided by F, 37.5. Similarly, Fi multiplied by Fj divided by F, making it 18.75. So these are the expected frequencies. If I look at the total, it is 360. These are the expected frequencies. These are the observed frequencies. Now I can compute my chi-squared value first by taking observed minus expected whole squared divided by expected. So I'll first compute this value across for all the rows, all the columns. Observed minus expected whole squared divided by expected. When I do a summation of all these things, this is my test statistic. This test statistic value is what I'll compare with my chi-square distribution. The chi-square distribution with 0.01 level of significance and 4 degrees of freedom is 13.27, whereas my computed statistic is 32.139. So this value is greater than 13.27, so I can very well reject the null hypothesis. So there is some kind of a relationship that is existing between people who have ability in mathematics versus their interest levels in statistics. So they are not fully independent. That's how we can very well look at R by C table and make some kind of conclusions regarding the possible relationship between two independent two variables within a particular sample of data. All right. Now, the next thing that we are looking at in this context, and another application with respect to hypothesis testing, is finding the goodness of fit. Again, here also we are using the chi-square distribution only. Here also we talk about the observed minus the expected whole square divided by expect, and we do a summation of all that. And so the process is still remaining the same. The application is different. But whenever we use the word goodness of fit in this context, my objective is to really evaluate whether a set of data that I am looking at coming from a random sample of a particular population having a given distribution. So I am assuming that the data is coming from, let's say, a Poisson distribution with some lambda. This is my assumed distribution. Actually, I sample the data, I collect it. Now I really want to see whether this data is coming from the same population or not. So this is my actual data and this is what is my assumed data or expected data. So we are trying to compare these two things using a chi-square distribution itself. So in this case, we are seeing whether this data is fitting this distribution more appropriately or not. We are testing the null hypothesis that a set of observed data, I have observed this data, comes from a population having a specified distribution. So whether this data is coming from a Poisson distribution or not. Again, the alternative that the population is not coming from this distribution, it is coming from somewhere else. So that is the typical test which we call as goodness of fit. In this case also, we use the formula Fi is the observed frequency, Ei is the expected frequency based on a particular distribution. So we are doing Fi minus Ei, expected actual frequency or observed frequency minus the expected frequency whole squared divided by the expected frequency. We sum this up across all the possible values and that is what we are calling as a chi-square. And as a part of the significance level, we'll look at the chi-square distribution. We'll find out the test statistic chi-square through this mechanism. And we will reject the null hypothesis when this value is greater than chi-squared with alpha level of significance m minus t minus 1 degrees of freedom, wherein m is the number of terms that are there in summation. Right, in this example, if we see there are 10 terms that are there as a part of the summation. So that is my m, and t is the number of independent parameters estimated. So what are all the things that I am estimating here? Based on the sample data, here I am estimating only the expected values. Right, so only the mean is what is getting estimated. So because of this reason, I am taking only one. But if I want, let's say in a Poisson distribution, there is only one parameter called lambda. So the estimate is only 1. So m will only be 1. But if I am talking about a binomial distribution, I have two parameters n and theta. I have to estimate both of them. In that case, my t is going to become 2. So that is the degrees of freedom that I really need to look at. Now from here, they are typically trying to assess, right, number of errors 0, 1 to 9. Let me take this data. They are talking about number of errors 0, 1, 2 to 9. Right. The observed frequencies are known, which are my F's, the observed frequency. 18, 53, 103, 107, 82, 46, 18, 10 to 1. So these are the observed frequencies. Now they really want to compare whether this is matching with Poisson distribution with lambda equal to 3. So if I want to look at lambda equal to 3, I can compute my Poisson probability e power minus lambda, right, multiplied by lambda power x, 3 to the power of x, divided by lambda factorial, factorial of x factorial. So I am dividing it by this. So this is giving me that the Poisson probabilities are something like this. When I sum it up, it's almost 0.9988 kind of stuff. Right? So these are my frequencies. Now these are my probabilities. Now I want to find out my expected frequency based on this. So I am taking my total. The total will come, the frequency is coming out through this, which is around 440. So I will compute my expected frequency, which is nothing but this number times 440, around 21.9. Right, so that's how I can, so I'll compute it as the Poisson percentage multiplied by the overall frequency. 21.9 is the expected frequency, 65.7, 98.57, 98.57. So these are some of the numbers that are coming out. These are my actual frequencies, these are my expected frequencies. So I can very well compute the actual frequency minus the expected frequency whole square divided by the expected frequency. So which is making the calculation something like this. Based on this, I am saying my chi-squared value, the computed chi-squared value is going to be 6.54. And now my critical value, where I will go into the rejection region, is nothing but I am going with a chi-squared distribution. Right, I am taking a chi-squared inverse. The probability that I am asked for is 0.05, so in Excel I'll take as 0.95. The degrees of freedom, okay, m minus t minus 1. Here my m is 10 and t is 1, so I can take it as 8 degrees of freedom. So in this case it is coming out as 15.5, right, whereas my computed value is 6.54, and because of this reason I will not reject my null hypothesis. I will not be able to reject my null hypothesis, so I can very well go ahead with saying that this data is not different from a Poisson distributed data. But at the same time, in some of these numericals, the way we work out is, if the expected frequencies are much lesser, right, in many cases I would be looking at the expected frequencies. If the expected frequencies are much lesser, right, I need where the expected frequency is greater than 5 in general. So wherever the expected frequency is less than 5, these two are less than 5, right? Even if I combine them, 3.6 and this is 1.18, these two are still less than 5. So I can think of integrating all these three. I can think of merging all these three into one itself. So which means here all these three will get merged into 13 with these values not being present, and here also I will change the stuff, right? If it is following a Poisson distribution, all these things I can aggregate to at this level. So I'll take a summation of all these things to this level, so making it 14.25. So here I can very well make it 14.25, and in a way I can delete these things as well. Now based on this, you could clearly see this is how the numbers are changing, right? I am computing it across all the layers. Now I am getting that the summation of all these values, F91 to F93, we don't require F91 to F93 here. Okay, so here if I am looking at the critical value now, I have only 8 different values because I have clubbed them. I will club all those things which have expected frequencies of less than 5. I'll club them to the nearest one. So I will get my critical value now with only m minus k minus 1. K is still 1. So with 6 degrees of freedom I am getting it 12.59, and because I have integrated it out here, this is what is coming out to be my calculated value. This is still lesser than my critical value. So because it is lesser than this, I am not able to reject my null hypothesis. So I can very well still make a conclusion that the observed data is not differing too much from a Poisson distribution with a lambda value of 3. But look at the Poisson distribution with a lambda of, let's say, 2.5 instead of 3. Right, I just change the numerical from 3 to 2.5 just to understand whether this makes a lot of difference or not. So the moment I have made it from 3 to 2.5, you could see that the summation is 48.5, whereas here it is working out to only 12.59. So the calculated value is much higher than the critical value that is determined through the table, which is a clear indication that the data is not coming from a Poisson distribution with a lambda of 2.5, but I can very clearly say that the data is coming from a Poisson distribution whose lambda value is around 3. So when I am comparing it with a Poisson distribution with a lambda of 3, I can say that this data which I got as a sample is a much good fit kind of a data, right? So that's how we try to analyze this particular goodness of fit, by comparing a sample of data against a population from which it is typically sampled, against the distribution based on the parameters of that population from which it is sampled. We can use the goodness of fit where we will be using the chi-square distribution only. So these are what I wanted to look at as a part of this session. We looked at the different critical regions, we did the various steps in testing the hypothesis, and we went ahead in terms of doing different tests concerning the means, difference between the means, regarding the variances, proportions, differences among the k proportions, looking at an R by C kind of a table, finding out the independence between the row and column variables, level of independence between the row and the column variables, and finally we also looked at a goodness of fit where we compared the sample data against the theoretical data coming from a particular distribution. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.